In Part 6 of Lecture 4, we will discuss interprocess communication. For processes to cooperate, they need some way of communicating. That requires that the operating system must support some sort of interprocess communication facility. The basic elements of any message system are the operations send and receive, which allow a process to send a message to another process, and to receive a message from another process. Implicit in this discussion is the fact that we have a means of opening up a communications channel between the two processes. We can view this channel logically in terms of the operations that we will use, or we can view it in terms of its physical implementation. We will only deal with the details of logical implementation at this moment. When we are ready to establish a link between two or more processes, there are a few questions that we must answer. What mechanism are we going to use to establish the link? Just as files processing requires us to open a file so that we can tell the system about its various properties, we need to do something similar when we establish a communications link. Many of the other questions need to be answered when the link is first established. How many processes are going to share the link? What is the largest number that we expect might share that link? Normally, we would expect that to be n processes, but it could conceivably be more. That affects how we handle synchronization. How many links will we allow two processes to share? What is the capacity of a link? If the link has no capacity to store, we may have to make a process wait before allowing it to send a message. If the link has a finite capacity, we may face the same problem of having to wait if we reach the limit of the link's capacity. But if the link has an unbounded capacity, we may not have to deal with waiting. How large can a message be? Is a message fixed size or variable size? A fixed size message system is easier to implement, but more difficult to use. The reverse is true of variable size message systems. Is communications one-way or two-way? It is important to remember that one-way message links must still provide a method for sending acknowledgments. Links can involve direct or indirect communications. We will discuss these at greater length. They can involve symmetric communications, where all processes are treated as peers, or asymmetric communication, where they are not. The buffering or temporary storage of the message may be explicit, where the sender has to handle the issues of buffering, or automatic, where all buffering concerns are invisible to the sender or receiver. Send by copy refers to transmitting a copy of the actual message. This is different from send by reference, where the location of the message is transmitted. Lastly, there is the issue of fixed or variable-sized messages, which make life easier or more difficult for the programmer or the operating system, as we discussed before. In the case of direct communication, we assume that the sending process sends the message explicitly to a particular process by name or identification number, and the receiver receives a message explicitly sent to it by a process identified by name or number. Implicit in this discussion is that exactly one link is established between the two processes. By the communication paradigm's very nature, it is understood to be unidirectional, but such a link could be bidirectional as well. If we were to implement the producer-consumer problem with a direct communication system, it would look like this. It is assumed that the producer waits for an explicit acknowledgement that its message is received. since the consumer has to be finished consuming before it is able to receive the message, the producer will wait. This ensues that the producer will never produce more than there is available storage. On the other side of the problem, the consumer receives the message from the producer. If there is nothing yet produced, it will sit and wait until the producer finally sends a message. Then, and only then, will the consumer consume it. This ensures that the consumer will wait unless there is actually something to consume. Indirect communication involves the use of a mailbox, where we explicitly name the buffer in which a message is held between the time that the sender sends it and the receiver takes it. In this case, it is possible for the link to involve more than two processes, although there is now a synchronization problem. We need to ensure that only one process can send to the mailbox at a time, and we may also need to control how many processes can read the message at once. Since the mailbox is a repository for messages, there is no reason why this can't be a bidirectional link. Links may or may not be capable of storing messages. This is important because this determines whether or not the process that is sending has to wait. If there is a zero capacity or a finite capacity whose limit has been reached, the sender will have to wait in order to send the message. On the other hand, if the capacity is unlimited, or if it is large enough that we do not have to worry yet about reaching or exceeding that storage limit, the sender can send the message without waiting. In communications, the two most important rules of thumb are: never assume that a message went and was received at its proper destination, and never assume that it was received error-free. Even messages on a single processor system between two processes can go astray or be garbled. One possible situation is where either the sender or receiver has already terminated. This could leave us with a sender trying to send a message that can never be received, or a receiver waiting for a message that will never come. One way around the problem is to let the process time out. That if the message or acknowledgement is not received within a certain time frame, we assume that it is not coming. We may choose to resend a pre-specified number of times before we assume that the other process is no longer there. This approach can also work if the message is lost. This situation is more likely on a distributed system than on a single processor system. If the message is received, it is possible to check for errors using either parity, cyclic redundancy check, or another error detection code. If the error is detected, then we can request that the message be sent again. Some codes may even allow us to determine what the error is and to fix it. While these coding methods are more expensive to implement, they save us the trouble of retransmitting a message. Mach is a message-based operating system. The kernel supports the creation and termination of tasks, which are essentially processes of multiple threads. Most communications are done by messages to and from ports, which are like the mailbox that we spoke about before. System calls are made by messages. When a new task is created, a kernel port and a notify port are created. The communications between the task and the kernel are carried out by sending messages between the ports. The ports are initially empty and messages are received in a first-in, first-out fashion, but a message can be reordered if necessary. In the event that a port is full, the thread that sent the message can either wait indefinitely, wait up to some maximum period of time, or simply cache the message. Windows NT was a modular system, which consisted of several subsystems which needed to communicate with each other. They would do this using the local procedure call facility, which is an indirect communication system. Ports in NT were objects and were visible to all processes. They provided the mechanism by which applications talked to each other. NT used 3 different methods of message passing, depending on what the client chose. The different methods were intended for messages of different lengths. Since NT used message passing for virtually all communications between subsystems, this tended to slow the system down.